science fictional things, as they were calling it, right? But then the whole idea of deep learning and its huge power started to help reinforcement learning. So one thing that I hope that you get up to this point, essentially, we are doing some sort of learning, but this is not the conventional machine learning that you knew in any sense, right? So it was basically trying to find out some sort of statistical conclusion out of a probabilistic environment, right? Which is still a sort of learning problem, but this is not the sort of computational learning that you know, where you basically use the magic of machine learning to just predict something that you have never seen. You don't do it really, right? For instance, if you want to know the value of one particular state, you need to see it enough number of times, right? If you don't see it, it's not going to, right? And there's no magic up to this point. So the magic is actually starting from here on, right? And this is what we call it deep reinforcement learning. What you see is that in deep reinforcement learning, the only thing that we do, we just add up a neural network to the basic estimation approach that we had. And using that one, we are now super capable of doing crazy things, which people did not think that is possible early days. So we talked about both of them. So model-based is over. This was helpful because it gave us the idea of Bellman equation, this recursive property of the environment. And model-free is over. I think now the terms here are very clear for you, right? So what is on policy, you know. What is temporal difference, Monte Carlo, SARSA, Q-learning, off policy, you know what they are, right? And now the thing that we want to do, we want to answer the second question, because I told you we have two questions. The first question was that, well, we don't know the environment, right? And then how we can do it? Well, we can estimate it, right? And by estimating it, we basically did model-free reinforcement learning, right? That was one part of the challenge. The second one is that what do we do if we want to just, if we are dealing with a large scale environment, right? And this is what we want to do in this chapter. So what we had up to this point is what we call a tabular reinforcement learning. And where does this word table or tabular come from? It's basically, as you can think of those value or action value functions that you have, as a sort of table, right? And the only thing that you try to just estimate the values inside that table. You would say, as long as I know that table, that's it, right? So what you do, for example, in all of those practical algorithms, you work with action value, right? And then this value is actually one inside this table of state and action, right? And you have m times n different pairs, so your table has m times n different entries, right? And you don't know the values inside these entries. You try to just do sampling based on those samples. You try to estimate them, right? And once you estimate them, you look at those estimates, you take them for granted, you just do the optimal policy, right? So that was the idea. This is why we call it tabular, right? So if you want to just visualize it, if you're just working with a value, then you have a value table, right? You would say my states are S1, S2. These are all possible states that I have, right? S1, S2 till Sn, all possible states that I could get to. And then I want to know what are the values. Well, initially I put all of them 0, then I keep on playing, right? And based on the samples I get, I try to improve the estimate of these values, right? And hopefully this is going to converge to something meaningful. I use that one to just decide my optimal policy. Or more practically, we usually work with the Q table, right? A Q table is simply the same thing in 2 dimensions. Any state, any possible action, then what you do eventually, again, you sample a trajectory in the environment, and each time you get into one of these cells, right? So you're in one state, you do one action, and then based on those samples, you just came up with some approach to estimate those values again, right? And if you can make this table very solid, like it converges to something low variance, then based on that, you start to decide, right? That was the whole idea. correct? So this is why we call it tabular, basically because we work with table, right? And this is nice. It gives us these results that, for example, this algorithm is going to converge, but the convergence always comes with this requirement that every single cell that you have here, you need to see it infinite number of times, right? Not infinite, practically large number of times, right? And if you think about a realistic problem, that is pretty much impossible, right? So this is the whole challenge now. The whole challenge is that what we did actually working, that is perfect. The problem is that we cannot really implement it in a feasible amount of time, right? So now, if we want to just use tabular, we can use temporal difference, we can use Monte Carlo. It doesn't matter which of them we do. At the end of the day, we need to see all of those state action pairs enough number of times, right? So say for each of them, we need C different samples. I don't know, 10, 100 samples that you can trust on the estimate that you get, right? If you want that, then you need C times N times M different samples, right? N times M is the number of pairs that you have. Each of them, you need to be there at least 100 times. So 100 N times M is the number of samples you need, right? And that N and M could be crazy large, right? So this is not happening. So in practice, you never get to even cover all the possible pairs in most cases, right? In many practical problems. So tabular reinforcement learning, that's nice, but the number is super sample inefficient. So the number of required samples you need in order to be able to somehow rely on the result that you get is eventually very, very large. And this is not possible in practice, okay? So you see the problem, right? So just I want to give you a couple of examples. Backgammon, you know that works, right? So you have different ways of playing it, right? And different ways of playing it, it means that you have different possible states. So there is, in total, roughly 10 to the power 20 different states, right? This is the number of ways you can play it, right? So this is the number of cases you can play. And say every time you have M actions, I don't care what M is. I just ignore it. I only talk about the states, right? And say that every single state, you can check it within 1 picosecond, right? It's a quite fast thing, right? You need to sort things out. This is one state. And then this taking like 1 picosecond is pretty much impossible, right? You start from that state. You play. You get one sample, right? This is the idea. If you do, for example, Monte Carlo, right? You again start from another state. You play. You again get another sample, right? Now, if you want to just get C samples for each state and every action that you could do there, then this is the amount of time that you need in seconds, right? And if you convert it into the number of years that you need, so if you want to collect enough sample, 3.2 times C times M samples you probably need to collect, right? Which is large, but you might say, okay, I am very interested in this game. I'm going to take this much time, right? No problem. Let's go for chess, right? I gave you this funny assignment. You just saw how many cases are there for chess, right? 10 to the power 120 was Shannon's estimate, right? So he said, like, the Shannon number says at least you can play 10 to the power 120 cases at least, right? But then that 10 to the power 120 was not smart in the sense that not all of the cases are a kind of case you play chess, right? Because many of them are dummy playing of chess. Then people started to just do this research. So it has its own research. How many cases of chess is there, right? And there is no concrete number, but there are better and better estimates.